Consider one-dimensional wave equation del square f by del t square equals c square del square f by del x square. In this equation, c is the speed of the wave, and this equation can be seen to have two types of solutions. If we are given any twice differentiable function h of a single variable, then hx minus ct is a solution of this equation. And again, if we have a twice differentiable function g, then gx plus ct is a solution of this equation. In order to see that hx minus ct solves this equation, consider partial derivative of h with respect to x. This will be equal to first derivative of h, which we denote by h prime, with respect to its variable. It's a single variable function, so h prime evaluated at x minus ct, and then partial derivative of x minus ct with respect to x, which is simply 1. Now if we evaluate its second partial derivative with respect to x, again it will be equal to double derivative of h with evaluated at x minus ct, and then partial derivative of x minus ct with respect to x, which is again 1. Similarly, if we evaluate partial derivative of h with respect to t, then it will be equal to derivative of h evaluated at x minus ct, and then partial derivative of x minus ct with respect to t, which is equal to minus c. And if we take second partial derivative of h with respect to t, then it will be double derivative of h evaluated at x minus ct, and then partial derivative of x minus ct with respect to t, which is again minus c. So we have minus c square here, which gives c square. So this is equal to c square, but h double prime x minus ct equal to double partial derivative of h with respect to x square. So we see that h satisfies this wave equation. Since the only difference between h and g is this sign of ct term, so we can see that g will also satisfy the wave equation, because the only difference in this derivation comes at this point when we evaluate partial derivative of g with respect to t. Then instead of minus c, we will get plus c. But then the double derivative of g with respect to t square will be same, because we will get a factor of c square in case of g also. So g will also satisfy the wave equation. Now if we plot these functions, suppose initially h is such that at t equal to 0, our function, this, if we consider this type of solution hx minus ct, then at t equal to 0 we have function h of x, and suppose initially it is localized at 0, and suppose for simplicity it has a maxima at 0. If we increase time to say t equal to 1, then our function will be hx minus c, t equal to 1. Now if we plot this function, this h is maximized at 0, so hx minus c will be localized at x minus c equal to 0, which gives x equal to c. So it will be localized at x equal to c, and its graph will look something like this. It will be localized at x equal to c at t equal to 1. Similarly, if we take t equal to 2, say, then our function will be hx minus 2c, and this function will be localized at x minus 2c equal to 0. So this will be localized at x equal to 2c, and its shape will look something like this. Means its shape will be same as before. I'm just trying to say that it will shift to the right, but its shape will remain the same. It will be maximized at 2c, and it will be localized at 2c. So this function hx minus ct, as time progresses, it is moving to the right. Its shape remains unchanged, and it's simply shifting to the right. So this is also called a right moving wave. hx minus ct is called right moving wave. Similarly, if we take the other solution, we take gx plus ct, then it's clear that it will be moving to the left. So suppose at t equal to 0, it is localized at 0, something like this. This is our gx at t equal to 0. If we increase the time to t equal to 1, then our function will be gx plus c, and it will be localized at x plus c equal to 0, which gives x equal to minus c. So this function will be localized at minus c. Its shape will be something like this. Similarly, if we take t equal to 2, then our function will be gx plus 2c, and it will be localized at x plus 2c equal to 0, which gives x equal to minus 2c. So we have minus c, minus 2c, and the shape of this function will be something like this. So this function is moving to the left. So this is called left moving function. We can also see this through a simple animation using Mathematica. Suppose we define our function f to be the bell curve function. So initially it is, suppose exponential minus x square by 100, it is localized at x equal to 0. Now we can use this manipulate function of Mathematica to see how it behaves when we plot, say, fx minus, we take c equal to 1. So fx minus t, if we plot fx minus t in the range, say, minus 50 to 50, and we vary t from 0 to, say, 50, and we take plot range to all. So if we plot this thing, we get this graph. So this is showing the plot of f x minus t at t equal to 0. So t equal to 0, it is localized at 0, and if we increase time, this is moving to the right. So this is our right moving wave. We have taken the velocity c equal to 1. So we have to increase t to its full value 50 for this graph to the shift fully to the right. If we increase the value of c, say if we take c to be 2, and then this graph will shift fully to the right when t is at around 25 value. Similarly, if we take x plus t instead of x minus t and then we increase time, this graph will be moving to the left instead of right. It is now moving to the left, and if we increase the velocity, it will be moving faster. So for half value of t around 25, t equal to 25, this graph has fully shifted to the left, while initially when we had x plus t, then in order for this graph to reach its leftmost position, we need to take t to the value of around 50. So this is left moving wave x plus t, and x minus t, fx minus t is right moving wave.